Hey, physics kids. Mr. Johansson here with the dynamics track. Right now I just want to talk about balanced and unbalanced forces. All right? I'm going to push this dynamics cart, get it going, the same way we would do our experiments with determining what the velocity is at the first, velocity second, and figuring out what the acceleration is as it's slowing down due to friction. But I want to talk about why it ends up moving in the first place. When I put my finger on it and push, I am pushing against the cart, and because there's no opposing force on it, I can push this cart and it will change its velocity while I'm pushing on it. If there was another block here and I'm pushing on it and the block is able to push back just as hard, it won't change its velocity. The time I'm pushing against the cart, it's accelerating. But once it's done, and my finger is no longer pushing on it, now what is it doing? Well, let's ignore the friction that's causing it to slow down ever so slightly, and we'll get to that in a second, but once I'm done pushing on it, it's just going to move away at constant velocity. Acceleration will only happen on anything, and this is universal, when there is an unbalanced force on it. If you see somebody, for example, you see me about to sit on this chair, all right? Well, when I sit on the chair, what's the chair doing now compared to what it was doing before? When I'm standing here, the chair doesn't have to push up at all. The chair is just static. It's holding up its own weight, but it doesn't have to push up any harder. But when I go to sit on it, that chair now, it has to push up exactly as hard as I'm pushing down. If you sit on it, well, you don't weigh the same as I. So the chair then has to push up that hard. But if the chair does not push up as hard as you're pushing down, the chair is going to collapse and you're going to fall down. Balanced and unbalanced forces. When you're walking on the floor, it's not just static. The floor is just not there and you're walking across it. That's not what's going on. When you're walking across the floor, you're pressing down on the floor. How come you're not falling through it? Well, let's look at what situation you'd have that would cause you to fall through it. If you came over to my house and I was going to play a trick on you and I dug a big hole in the ground and put some sod over it, I said, "No, come here for a second." And you walked over, wah, you fall through that hole. Why did you fall through it? What is that top of the ground not able to do that the rest of the ground is able to do? Well, maybe you could see it. Where I dug out, that fake sod on the top, when you stand on it, can it push up? No, it can't. So you're pushing down, nothing else is pushing up, so you fall. You accelerate downward. So what's the ground doing with me right now? Well, I'm pushing it down. Is it pushing up? Of course. Consider a situation where you have a really big, heavy object sitting on a concrete surface. If you just have a thin layer of concrete, will that work out okay? No, it'll crack the concrete. It'll press it down and compress the ground until the ground is able to push up as hard as it's pushing down. I always use the example of when you have a huge airplane like an A380 come in for a landing. Can it land on any old runway? Well, no. If you're going to take an airplane that big and land it on a runway, the runway has to be specially designed. What's the special thing? It can push up as hard as that massive airplane is pushing down. We have to engineer everything like that. Our bridges have a maximum weight. The maximum weight is the heaviest thing that could go over the bridge, and the bridge can still push up that hard. Imagine taking a long 2x4 and putting it across a stream and walking across it. Well, the 2x4 is going to sag and probably break. Well, you already know that. So this is intuitive stuff. If you're trying to get a bridge across a stream, you have to make a bridge that can push up as hard as anything going across will push down. If you're trying to make a bridge for a car, that's an entirely different thing than making a bridge for a person. A bridge for a person, a couple 2x4s angled this way with some boards on top, you might be able to get away with that depending on how big a distance you're trying to span. The bigger the distance, the more you're going to need to push up because you're acting like a lever in the middle. But everything works this way. If we look at a balance, try a triple beam balance. All right, take a look at the triple beam here. All right, so how does the triple beam balance work? All right, it's all balanced now. How does that, talk about unbalanced forces. So how does the triple beam balance work? Well, why did it go down? All right, why did that plate go down? And what would make the plate go back up? This is literally a balance. When I put as many grams on this side, and they're all being pulled down, all right, I think I have really more than 100 grams. All right, so it's close. 90 grams. So the idea here is, however hard this is pushing down the aluminum cube, it would push down and force that up. So now I have moved the masses over and they're on a lever. So now this is pushing down as hard as that is pushing down, and the thing is in balance. Let's take a look at one more thing I want to show you with this. All right, that's the front of a classroom here. Take a look at this odd little device here. I like this a lot. When you first look at it, you're just thinking like, I just have some weird toys. And I do. But this is an especially good weird toy. I'll put it in the sink drain so you can see it. All right, so what's going on here? Well, take a look at the distance between the two balls here. They're being supported by this spring. The spring can push up. How hard does this spring have to push up? Well, hard enough to deal with the weight of this ball. How hard does the spring down here have to push up? Right? If I take this up and just hold it so you can see it. How hard does the spring on the bottom have to push up? Well, the spring on the bottom has to deal with all of the weight on top of it. So the spring on the bottom, you'll see, is compressed far more than the spring on the top. Why? Because that spring on the bottom has to keep pushing up until it's pushing up equal to the weight of all of these on top of it. The spring on the top just has to hold the top ball. So when we look at the floor or the desk or things like that, this desk, when you sit on it, hard to measure, but it will deform ever so slightly. And it's kind of like a spring. It will deform, and in its deformation, it starts pushing up harder and harder. And it will push up harder and harder until it equals your weight. So that's balanced and unbalanced forces. If you step off a step, you step off a step, you fall down to the next step. Why do you fall down? You're not just falling down, you're accelerating down. Why? There's nothing pushing up on you. There's no force to balance your weight. When you get down to the next step, why do you stop? Well, because that next step is pushing up on you equal to your weight. So if you're in balanced forces, you're not accelerating. If you're in unbalanced forces, you're accelerating. So that's how the world works. All right, there's actually atomic forces. When I'm walking around the floor, I'm pushing those atoms down and they get a little closer to each other. The electrostatic repulsion increases until it's pushing up as hard as I'm pushing down. All right, hope you got that. Thank you.